All right, let's get started. Then now we'll explore first the difference between PTP and linear movements. Um, as we've discussed earlier, PTP is a joint-based movement where the robot optimizes its path for efficiency. The robot chooses the most efficient joint configuration to reach the target. What does optimized path means? It means that the robot moves in a way that minimizes the strain on its joints. For example, you have point 1 here and point 2 here. When using PTP, the robot will move from point 1 to point 2 via PTP. And here's what happens. It would follow this curved path by adjusting its joints to reach point 2 in the most efficient way possible. Notice that even if the ideal path is a straight line, the robot prioritizes joint efficiency. It moves out of this predefined area and you set and will create a non-linear trajectory between point 1 and point 2. This results in these angular motions shown here. It still reaches point 2 just like a linear motion would, but with less mechanical stress. The advantage of it: faster movement and reduced wear on joints, so you have a longer robot lifetime. PTP is generally faster because it avoids overloading accesses of the robot while executing the movement. However, there's a critical drawback when using PTP, and the first one is collision risks. So if this area has a box or a tool or another robot passing close, using PTP from point 1 to point 2 could cause a collision mid-path. This is where lean motions become essential. If the robot uses PTP to move from point 1 to point 2, it might collide somewhere with obstacles along its non-linear path. Now, how does lean motion differ? In lean motion, the robot follows the gray dashed line, representing a strict linear path. It moves directly from point 1 to point 2 in a straight line, no curves, just a precise linear trajectory. With PTP, the robot starts at point 1, moves to point 2 using the most efficient joint configuration freely without overloading the axis. It's faster, but it runs into an unknown trajectory. Okay, so PTP is joint efficiency over linear movement. So if you use PTP, you cannot predict the movement exactly. You only can see it during testing. However, linear motion, as I said, ensures a straight line path. But forces in the axis to maintain such a precision increases a lot of the mechanical stress of the robot. This can wear down components over time. So if another critical point of linear movements is depending on the robot's current position and the end position, a linear movement might fail. If the robot can't maintain a straight path due to the joint limits or obstacles that might be on the way, for example, if the robot is far from point 2 and you command a linear motion straight from point 1 to point 2, it might not reach the target. But with PTP, even if the robot is positioned far away from one point to each other, it will reach exactly the point. However, a lean motion from an awkward position where the robot is twisted up, the robot might throw an error. And to resolve this in scenarios where, depending on the robot's position, commanding a linear motion might fail, because the robot cannot maintain a perfect straight path to the target point you've first specified, so it is crucial to consider a program structure and account for these factors. So deciding when to use PTP versus linear motion is key to every movement that a robot should do. For example, suppose I create a linear point here. If the robot is in this position and I command it to move to point 1, it will follow a strict path here, as shown by the cursor here. Starting here, it moves linear to point 1. Then proceeds to point 2 along the gray dashed line. However, if the robot is positioned far from point 2 and you command PTP, it will freely adjust all axes to reach the target, potentially invading other workspace, of course, but with linear motion, maybe this movement would fail. It doesn't allow to do a straight path. So a common solution is to manually reposition the robot closer to the intended path. For instance, if you manually adjust the robot's position for maintenance, reposition it near the target point with a better placement of the joints before executing the lean movement, it may be not throw an error then. So it depends always the position of your robot, the position of the TCP, and the position of the ending point. And important, always validate both directions. Keep this in mind. Typically, we have two types of motion, PTP, which is and linear, as shown here, okay? So for example, a PTP motion from point 1 to point 2, followed by a lean motion to point 3. Imagine we have point 1 here, and then we do PTP to point 2, following this trajectory. Then we need to go to point 3, which is down here, for example, but with a linear movement. However, a critical point, when the robot moves via TCP and executes a linear movement to another point in space, with point 3, another key consideration. When programming, we often focus on forward motion, but overlook the reverse motion. For instance, if the robot moves from point 1 to point 2, and you command to return to point 1, the reverse path must be validated. Executing a reverse motion backward in a program can introduce risk if you don't know what type of movement the robot will do. Okay? During the reverse motion, the PTP will adjust freely its joints again, so the motion will not be exactly the same. So the path may not be correct. So this curve is from one side, but the other side may be a different trajectory. Ideally not, but could be. So, however, every time you need to test your programs running both on the forward direction and in the reverse direction to ensure that the robot doesn't face problems during this time. So if I do a PTP to point 2 and a linear to point 3 here, if the robot's at point 3, and you command to return to point 2 via a reverse, and it should follow the same strict path as a linear. So if I do a linear movement from point 2 to the point down here, assuming point 3 is here, the robot will move back to point 2 via a linear movement if I play this on reverse. But if I use a PTP instead, I have, of course, this whole area and this unpredictable movement that could cause problems. Okay? So run the program backwards, command the robots to retrace its steps, and always, so if the robot's on point 3 and you command it, for example, to return to point 1, the PTP motion might create a collision risk. So make sure that every possible path that your program might face is tested and validated, so you avoid collisions. Okay, so always remember this movement from point 3 to point 1 must be taken into consideration, even though it's not a regular a regular movement of your software. It should go to point 1 and 2 and then 3, but in some cases you may be on point 3 and you set a movement to point 1, but this could be dangerous. So always test in forward, reverse, and all the possible scenarios of movements that the robot might face when running your program in a unknown way, for example.